We are looking at a paper today titled SM4RT, Learning Structured Motion Geometry for 4D Reconstruction,
Right.
by Xingho J. Lin and a team of researchers from Tsinghua University.
Right.
And if you build machine learning systems or, work anywhere in computer vision, the absolute headache of 4D reconstruction.
Oh, it is a nightmare.
It really is. I mean, standard methods basically track millions of 3D points completely blindly, just frame by frame.
Totally independent points.
Right. And the result is that objects usually look like they're melting or just tearing apart because the model has zero concept of basic physics. But today's paper throws that entire approach out the window.
It's a total paradigm shift.
Exactly. They introduce something they call structure of motion. So instead of millions of independent points, SM4RT learns a compact set of motion bases using 6D twists in the C3 Lie algebra.
Which is mathematically beautiful, by the way.
It is. And it does this in a single forward pass from just a monocular RGB video. It jointly infers both the scene geometry and these shared motion bases. So it basically drops the degrees of freedom off a cliff, and it preserves rigid body kinematics without any test time optimization.
And the reason you, the practitioner listening to this deep dive into AI paper slop, need to really pay attention to this is that we're looking at a fundamental shift in spatial computing.
Yeah.
We are finally building a bridge between mere point tracking, which is honestly functionally just guessing where individual pixels might go, and true physics-aware dynamic scene understanding.
Right, because it's moving from neural networks that just sort of memorize arbitrary pixel trajectories to networks that actually comprehend the structural reality of a solid object in 3D space.
Exactly. It's about actually understanding the object.
So let's actually dig into why that point tracking approach is so fundamentally flawed. Because, it is currently the foundation for state-of-the-art models, things like Trace Anything or Any4D or even D4RT.
Yeah, they all rely on it.
Right. And if you look at the math, they formulate motion strictly as point-rise trajectory estimation. You take a source frame, you locate a point at time 0, and then the network just tries to predict a displacement field for every single subsequent frame.
The equation governing that is, it's about as simple as it gets. The position of a point at time t simply equals its position at time 0 plus delta t.
Right.
That is the absolute standard. But I want you to just think about what that requires computationally.
It's massive.
It really is.
Right.
You are operating with 3 SHW degrees of freedom.
So just to break that down, that's 3 spatial coordinates multiplied by s for the number of frames times h for height times w for width.
Exactly.
To put that math into perspective, if you are analyzing just a standard video clip, you are literally asking the network to calculate millions upon millions of completely independent variables.
And it places absolutely no constraint between pixels that physically belong to the same object.
Right. It treats every single pixel on, say, a moving car's door as totally independent from the pixels on that exact same car's roof.
Which creates this massive structural gap in the network's understanding.
Yeah.
There is zero self-constrained mathematical coupling.
It honestly seems like trying to animate a 3D character in a video game by independently calculating the physics for every single atom in their arm.
Wow, yeah, that's a great way to put it.
Rather than just, rigging a bone skeleton and moving the bone, it's just massively over-parameterized.
It is.
But wait, I do have to challenge this premise for just a second.
Okay, go for it.
Because if we look at the autonomous driving industry, right? Companies are relying heavily on this point-wise tracking for localization right now.
They are, yeah.
And it's keeping cars on the road. It's avoiding pedestrians. So if it works well enough to drive a literal 2-ton vehicle, why do we need to completely overhaul the underlying math?
Well, it's because localization and dynamic reconstruction are 2 entirely different tasks.
Okay, how so?
Well, if your only goal is to draw a 2D bounding box and just roughly predict where a pedestrian is going to be in the next, say, half second, tracing independent points totally gets the job done.
Because you just need the general direction.
Exactly. The system just needs an average vector of movement. But, and this is the crucial part, the moment you ask that exact same model to interpolate intermediate frames or extrapolate into the future to predict really complex interactions, the pointwise method catastrophically fails.
Right, because of the jittering.
Yes, objects jitter, they warp. The bumper of the car drifts in a slightly different direction than the windshield.
Because the network literally doesn't know it's a car.
Exactly.
It just thinks it's a cloud of independent pixels that happen to be moving in roughly the same direction at that specific moment.
Right. The network has no internal representation of a rigid body.
Wow.
So when you ask it to predict a state it hasn't explicitly memorized from the training data, those independent points just drift. Accurate point-wise displacement absolutely does not equal meaningful dynamic understanding.
Because real-world objects obey rigid body kinematics.
Exactly. When a car rotates around a corner, those aren't just random coordinate shifts. The entire vehicle shares a single common motion structure.
Which is the perfect entry point for the paper's main contribution. Because the researchers essentially decided to mathematically force the neural network to respect that physical structure.
Yes, they did.
And they call this structure of motion, or SOM.
Right.
So instead of millions of independent points, SM4RT assumes the scene's motion can be decomposed into a highly compact set of n motion bases.
And in their experiments, they set n to just 10.
Just 10. 10 motion bases to explain the entire dynamic scene.
It's incredible. And to make this work, each of these 10 bases is represented as a temporal sequence of 60 twists in the C3 Lie algebra.
Okay, I want to pause on the C3 Lie algebra thing for a second.
Sure.
Because I know a lot of engineers hear Lie algebra and their eyes immediately just glaze over.
Oh, absolutely. The math can get pretty dense.
But intuitively, a 6D twist is essentially the mathematical DNA of a movement, right?
Yes. It's a highly compact vector containing 3 components for translation and 3 for rotation.
Calling it the DNA of the movement is honestly a fantastic way to visualize it.
Thanks.
Because in standard 3D coordinate space, calculating complex rotations gets messy incredibly quickly.
Right. You run into gimbal lock.
Exactly, gimbal lock or just weird nonlinear distortions. But Lie algebra operates in the tangent space of the rigid body transformation group, SE3.
Okay.
And that allows you to perfectly and linearly describe a continuous rigid body motion pattern without any distortion whatsoever.
That's so clean.
It is. And then to connect the dense scene back to these 10 bases, SM4RT generates time-shared assignment weights.
Right, so every pixel gets a weight distribution determining which of the 10 bases controls its movement.
Exactly, and those assignments stay consistent across all the frames.
So if I'm breaking down the logic of the network here, it is essentially answering 2 distinct questions.
Okay, let's hear them.
First, it asks, which pixels move together as a single unit? Right, that's the time-shared assignment map.
And then it asks, how does that specific grouping move through time?
Yes, and the answer to that is the temporal sequence of C3 twists.
So by decoupling what moves together from the how it moves, the effective degrees of freedom just completely collapse.
Massive reduction. We go from that huge 3SHW equation we talked about earlier down to just NHW for the assignment weights plus 6SN for the motion bases.
So you are dropping from millions of variables to literally a few hundred.
It shifts from being severely over-parameterized to being incredibly parsimonious. Any points sharing the same dominant basis are mathematically bound to follow the exact same temporal rigid motion trajectory.
And because they are operating in this C3 twist space, it naturally solves that tearing and stretching problem we just talked about with interpolation.
It completely eliminates it.
Because, I mean, if I try to guess where a moving car is halfway between 2 frames using raw point tracking, I'm basically just drawing a straight line between point A and point B.
Right.
And if the car is rotating, straight linear interpolation means the car will physically shrink during the rotation.
Yeah, imagine looking at a coin spinning on a table.
Okay.
If you track a point on the edge of the coin and just draw a straight line through the center to its position on the other side, the coin just flattens into a line.
Oh, wow. Yeah.
It entirely loses its rigid structure. But by interpolating the twists in the Lie algebra instead, and then using the exponential map to convert that back into a finite rigid transformation in SE3, the structural integrity is perfectly preserved.
So the car stays a car.
And the coin stays a coin.
Okay, the mathematical theory here is incredibly tight. But for the engineers listening who actually have to build these systems...
Well, theory only goes so far.
Exactly. How do you actually implement this in a neural network architecture? Especially doing it in a single forward pass from a 2D video without falling back on iterative test time optimization?
It's a great question. Let's trace the dual decoder architecture, and we can start with the backbone.
Sounds good.
So the foundation relies on a geometry foundation model. You feed the input video in, frame by frame. Every frame is patchified and encoded using a pre-trained DynoV2 vision transformer.
Right, to extract those rich localized features.
Exactly. And then that sequence feeds into a geometry-aware backbone. Specifically, they use depth anything V3 or DA3.
VA3, yeah.
And DA3 utilizes local global attention mechanisms to produce latent geometry tokens that are heavily enriched with 3D structural cues.
So the DA3 backbone basically gives the network a really robust understanding of the static 3D geometry of the scene.
Right, it knows the depth and spatial relationships.
And at that point, the architecture splits into two parallel branches.
Yes.
The first branch is the scene geometry decoder, which is fairly standard. It has a camera head outputting per frame extrinsics and intrinsics, and a depth head outputting dense depth maps.
Yep, very standard.
And then you unproject those using the camera parameters, and you suddenly have your anchored world coordinate point cloud for the source frame.
So the scene geometry decoder builds the stage, essentially. But the second branch, the motion geometry encoder and decoder that branch, animates the actors.
Okay, I like that analogy.
Because the DA3 backbone encodes great static structure, but it doesn't natively capture motion-specific interframe cues.
Right.
So to fix this, they introduce end motion tokens with per-frame time embeddings. These tokens first cross-attend to the source frame geometry tokens, but the real critical architectural innovation here is a mechanism they call intermediate injection.
Yes. I was looking at the diagram for intermediate injection in the source material, and it is fascinating.
It's so clever.
Because as the motion tokens are passing through 4 layers of frame motion attention, the network is pulling intermediate geometry tokens out of the DA3 backbone and projecting them directly into the motion attention layers midstream.
Exactly.
It seems like they're basically forcing the motion tokens to constantly double-check their math against the 3D physical reality of the scene.
They absolutely are. I mean, without intermediate injection, the motion tokens might try to optimize for 2D pixel movement in a vacuum, completely ignoring depth or object boundary.
Right, which gets us right back to the original problem.
Yes, exactly. So by constantly injecting the structural reality into the motion attention layers, the tokens aggregate dynamic cues while remaining firmly grounded in the physical geometry.
Okay, so that gets us our enriched motion tokens.
Yep.
But how do we get from those tokens to the actual C3 twists and assignment weights?
So the motion geometry decoder splits into 2 specialized heads. Let's look at the base head first.
Okay.
This uses a dense prediction transformer to produce the per pixel base assignment weights. But the activation function they chose here is what really caught my eye.
Yeah, they apply a SparseMax activation function along the end dimension rather than just a standard softmax.
Softmax would be a total disaster here.
Really?
Because softmax naturally hedges its bets. If you use it, the math will want to give every pixel a tiny fraction of every single motion base just to minimize the overall statistical error.
Oh, I see. It blends them.
Right. But SparseMax acts as a hard mathematical threshold. It actively promotes sparsity, so it forces the network to cut off the noise and make a definitive choice about which rigid body a specific pixel actually belongs to.
Okay, so it's sort of like the sorting hat in Harry Potter.
Oh, that's good.
You know, you can't be 10% Gryffindor and 90% Slytherin. SparseMax forces the pixel into a specific house.
That's exactly what it does.
And then you have the second head, the motion head, which is an MLP that decodes those tokens into the actual temporal twist sequences.
Right.
So you take a weighted sum of the temporal bases using the assignment weights, apply the exponential map, and boom, you have your point-wise rigid transforms for the entire scene in one forward pass.
But an architecture like this, no matter how good it is, will fail instantly without the right loss functions.
Oh, for sure.
Because if you do not penalize this network correctly during training, it will find a mathematical loophole and take the path of least resistance.
Especially because they don't have dense, manually annotated 4D tracking data for every single frame to train on.
No, that would be impossible to get.
Right, so they have to rely on basically behavioral psychology for the neural net.
I love that phrasing.
These loss functions act as guardrails, nudging it away from lazy shortcuts.
Yes, exactly.
So the first one they use is entropy regularization. And we just talked about SparseMax forcing a choice, but what shortcut is the entropy loss actually preventing?
Well, it acts as a secondary enforcer against diffuse distributions.
Okay.
Because even with SparseMax, during the really early training epochs, the network might still try to blur a pixel across multiple motion bases just to minimize the raw tracking error.
It's trying to cheat.
It is trying to cheat. So the entropy loss heavily penalizes that ambiguity. It forces the weight distributions to be incredibly sharp.
It mathematically demands that a pixel belongs to one distinct moving object.
Exactly. It forces commitment.
I like that. The second loss is pseudo-background regularization. My read on this is that it sort of builds a firewall between the world itself and the actors moving within the world.
That's a great way to look at it, because just look at the visual composition of most videos, right?
Yeah.
The static background usually occupies the vast majority of the spatial area.
Yeah, mostly walls or roads or sky.
Right. And a lazy neural network will frequently try to use that dominant background motion base to help explain parts of the dynamic foreground objects.
Oh, I see.
It lets the background math sort of bleed into the moving things to smooth out the error gradients.
Which completely ruins the isolation of the rigid bodies.
Yes.
So the pseudo-background regularization identifies the dominant static background base by literally taking the mode of the dominant assignment indices.
Yep.
And then it mathematically penalizes the network if it tries to assign that specific background base to anything in the non-background regions.
It strictly enforces that boundary.
That makes total sense. And then the third loss, twist singularity regularization, is perhaps the most important for preserving kinematics, I think.
Oh, absolutely. Because a dense SE3 motion field can sometimes lazily collapse into translation-only motion.
Because calculating just a straight line shift is way computationally cheaper for the network than calculating the complex rotations of a twist.
Exactly. The network wants to avoid rotation if it possibly can.
Right.
So the singularity loss introduces a translation supervision that explicitly prevents the model from ignoring those rotational components.
Wow.
It forces the network to learn true rigid body kinematics rather than just lazily sliding points around on a 2D plane.
So we have a robust theory. We have an architecture that handles everything in a single pass.
Yeah.
And we have loss functions that prevent lazy math.
We do.
But for the engineers out there looking to deploy this, performance is basically the ultimate metric.
It always is.
How does this actually run on a GPU compared to the point tracking competition?
The efficiency metrics are actually highly competitive. Running on an NVIDIA RTX 5880, SM4RT completes a full 4D reconstruction in just 2.86 seconds per sample.
That's really fast.
It is. I mean, compare that to a complex method like VDPM, which takes almost 65 seconds for a full pass.
65 seconds versus under 3.
Exactly. And even the faster methods like NE4D take about 4.5 seconds. And SM4RT maintains a very manageable GPU memory footprint too, around 15.7 gigabytes.
So 2.86 seconds is incredibly fast, especially considering the structural constraints it's calculating. But the paper also details an adaptive variant in the benchmarks.
Yes, SM4RT adaptive.
What actually changes in the adaptive version?
So the adaptive variant introduces an optional post-processing step, and this is for applications that require absolute strict rigidity. After generating the assignment weights, it applies HDB-exact clustering.
Okay, HDB is scan, which is a density-based spatial clustering algorithm, right?
Correct.
It finds core groups of high density and then expands clusters outward from them.
Yes, so it adaptively determines distinct class regions based on the weight distributions.
Okay.
And then it replaces the individual motion base of each masked region with the average value of its assigned region.
Got it. Does that slow it down?
It does. Inference time jumps to about 11.6 seconds because of the clustering overhead.
Okay.
But the trade-off is that it enforces incredibly strict rigid regions, wiping out almost any residual dynamic deformation.
Speaking of deformation, we really need to talk about how the researchers actually prove their model works better.
Oh, this is one of my favorite parts of the paper.
Because standard tracking metrics have a massive blind spot here, right?
Huge blind spot.
Things like average Jacquard or average percent of points within delta, they just measure if a point ended up near its target destination.
Right, and those metrics completely fail to capture structural integrity.
Yeah.
Like, if a network tracks the front bumper and the rear bumper of a car and it places them accurately in the final frame, standard metrics give it a near-perfect score.
But if the model allowed the car to stretch to 50 feet long in the intermediate frames before snapping back, the reconstruction is completely useless for spatial computing.
Useless.
So to solve this, the authors literally went outside of computer science entirely.
They did.
And they borrowed math from material science.
They brought in the von Mises strain tensor from continuum mechanics.
Wait, isn't the von Mises strain tensor what structural engineers use to calculate whether a steel beam is going to warp or yield under physical stress?
It is exactly that.
That is wild.
The authors realized that evaluating a point cloud for non-rigid distortion is mathematically identical to evaluating how a physical material stretches or shears under physical stress.
That is so smart.
Right. So they apply an affine alignment between the source and target point clouds for a rigid segment, and then they compute the Cauchy-Green deformation tensor.
The Cauchy-Green tensor basically measures how much the square of the distance between nearby points changes due to deformation, right? Because if the object is perfectly rigid, the distance between any 2 points on it should obviously never change.
And from that tensor, they derive the von Mises equivalent strain metric for the point cloud. It is a brilliant cross-disciplinary way to mathematically prove that their dynamic reconstructions aren't, just turning into jelly.
And the benchmark results absolutely reflect that rigor.
They do.
I mean, SM4RT achieves state-of-the-art tracking on benchmarks like TAPDID 3D and WorldTrack, but it absolutely dominates on the von Mises metric.
Dominate.
It objectively proves that it preserves structure better than any existing point-wise method.
And what is truly fascinating here is that it achieves top-tier point tracking, not in spite of its rigid body constraints, but actually because of them.
Right.
When a network actually understands structured motion perception, its trajectory estimation naturally becomes more accurate. The two concepts are mutually reinforcing.
That makes perfect sense. So summarizing this for you listening,
Right.
SM4RT isn't just an incremental update trying to squeeze 2% more accuracy out of a standard displacement field.
Not at all.
It is a fundamental rethinking of how AI should perceive motion entirely.
Yes.
By embedding the C3-Lie algebra directly into a transformer architecture, we get fast, physically grounded 4D reconstruction from just a monocular RGB video.
The network actually understands what a solid object is.
Right.
It completely solves the rigid body problem.
Yeah.
But, if we pull back and look at the broader implications for AI, this raises a highly complex question.
What's that?
Well, SM4RT enforces rigid body physics flawlessly, right?
Yes.
But the real world is not constructed entirely of rigid bodies.
That's true.
We are surrounded by fluid dynamics. We have cloth deformations that fold and wrinkle infinitely.
Yeah.
We have complex physical collisions where energy transfers, materials yield, and objects shatter into totally unpredictable pieces.
Wow, yeah.
So if the ultimate goal of AI is to build true comprehensive world models, how do we extend this structure of motion paradigm to handle a glass shattering on a floor or a wave crashing against a rock?
Because in those specific moments, the rigid body assumption completely breaks down.
Exactly. Are we going to need to design separate, specialized architectural motion bases for every different state of matter?
That is a massive architectural challenge for the next generation of researchers, and honestly, a perfect thought to leave on. Thank you for joining us for this deep dive into the source material on AI paper slop.